Okay. So 8.4 triangle proportionality theorem. I just showed you a little bit about one, but let me just make a triangle. So we have this triangle ABC. And now I'm just going to draw a line through that's parallel to BC. We'll call this ABCDE here. Okay, so if you look at the big triangle ABC in comparison to the little triangle, are they proportional? Are they similar triangles? I got 2 mm-hms and 20. We're not talking to you, Mr. Collards. Are they proportional?
Yes. Yeah.
All right. Okay. How? How do we know?
Because those two angles on the parallel lines are corresponding angles.
Like these two?
Yeah, so they're congruent. And then the one below that, they're
Like those two?
yeah, they're congruent. And then it's congruent to itself.
And then the one they share. Okay. So we've got angle, angle. Well, I suppose angle, angle is what we call it. We don't call it angle, angle similarity. And we always just say angle, angle. So we have the two triangles similar to one another. Now, here's the thing. If a line parallel to one side, to any of the three sides of a triangle, intersects the other two sides, then it divides the two sides proportionally. Now, here's what that means for you guys. Not only does it create two similar triangles here, but AE over EB is going to equal AD over DC. And you'll notice here, I'm not talking about the full sides of the triangle. I'm just talking about this piece over EB, that ratio. You notice this is quite a bit shorter, isn't it? Does it look like maybe it's a third as long or so? Thirdish? Okay. AD over DC. Does AD also look like it's about a third as long as DC? Okay. So that proportion holds true. We could also do it this way. AE over AD. AE over AD. What's it going to equal? No. Not you guys can't all just sit there and quietly let him say it. Look at the picture. AE over AD. What's it going to equal? Everyone say it together. EB over. There you go. Okay. This is the triangle proportionality theorem, and its converse. Think about what its converse might say. So I've got this triangle. I have it centered up there. Okay. And I draw a line through it like this. And this is I don't know, this one's 3. This one's 3. This one's 4. This one's 4. Are the sides proportional?
Yeah, so
They're proportional, aren't they? What does that tell us about these two lines?
they're parallel.
They're parallel. And it's not always 3, 3, and 4, and 4. I mean, I could have drawn it up here and said this is 1 and 5. I suppose this one, what do we got here? 8? Yeah, I kind of, so this might be 2 and, well, that's not so pretty, is it? What would they have to be? If the whole thing's 8, this is an actual problem, but I'm just now interested. If the whole thing's 8, and this ratio is 1 to 5, could you guys figure out how long these pieces are? A little piece here, and then this whole piece down here. You've got to have this 1 to 5 ratio, and it's got to add. They've got to add up to 8 as well. So this is something we're going to talk about today, but let me erase these. here's what we can do. Let's just give this little short piece a name. George? Fred? What would you like to call it? Bob? Okay, so what do we call it in math? Easier. X. Let's call it X. Okay? Well, how about this piece down here? Can we give it a name? What do you want to call it? Y. I don't want to call it Y. I want to call it X. I don't want two variables. Can I call this one X also? No. It's not. It can't also be X, can it? But what's the length of the whole thing? 8. And this bit's X. So how long's this piece? Wait, you guys can still see that, can't you? I'm going to get rid of that. It's got to be 8 minus X. This is a big-time trick for mathematicians. I mean, two different things. I don't know how long either of them are, but I gave them both a name, but I only used one variable. Can you see how that's a really good thing? Right? That is a good thing. And so now we know that 1 over 5 has got to equal x over 8 subtract x. Is this something you guys can solve? What do we get? Come on, you can all do it. How come I only heard one of you do it? Okay, so 8 equals 6x? 4/3? So that's 1 1/3. Take that away from 8, that'd be 7 6 2/3. Right there. Okay? We'll talk more about that as we go along. Let's talk about now the parallel lines theorem. So we've done a lot of stuff with parallel lines. I'm going to draw 3 parallel lines, but they don't have the spacing the same, but all 3 of them are parallel to one another. Now I'm going to draw a couple of transversals. And I'll just name this piece A and B, and this piece X and Y. So here's the parallel lines theorem. If 3 parallel lines intersect 2 transverse, then they divide the transversal proportionally. They divide the transversal proportionally. Is A the same length as X? No. How about B and Y? Are they the same length? But when you look at it, look at the ratio between A and B. See how, just eyeball it. See how A is about twice as long as B? Well, what about X compared to Y? Yeah, it has that same proportion. And actually the proportion is written here. All we have to do is put an equal in between and put a fraction line there. A over B equals X over Y. Or A over X can equal B over Y. You can do it that way as well. Okay? So, gosh, look at example 3 on 448. You got Main Street. You have 2nd Street. And then you have South Main. Kind of spaced out like this. Got a transversal. Got a transversal. This is 120 yards. This is 300 yards. This is 150 yards. Can you guys find X? Any luck?
Yes, it's fixed.
Really?
So is your other problem. Left-right problem.
Oh, really? I just trained myself to go the opposite direction. Now I'll have to retrain my brain, will you?
Fix that.
You are, no, you're good.
I'll show you.
Okay.
You'll right click out here on the desktop somewhere, go to display settings. See this thing here? If you put it over here,
Oh, I didn't know I
hit
could grab that and
apply,
drag
then
it
it's
over.
here. If you put it over here and apply those changes, you now have across there. Where do you want it?
No, yeah, I want it like this, like you have it now. So when I move to the mouse to the right, I'm on it.
Okay.
Sweet. And what was the problem with the laptop?
The driver was hosed up.
Oh.
When we put in these new wireless access points, I've had to go around to a lot of these notebooks and reload the wireless driver because I don't know.
Well, I wonder if Pete's going to have the same problem. I don't know.
Probably will.
Okay. All right. Well, thank you very much.
Guaranteed for 5 years until you need it.
Until I need it.
Yep.
Okay.
Based on need.
All right, guys. Triangle angle bisector theorem. Triangle. Should I construct the angle bisector to help you guys remember how this works? So if I'm going to, oh man, I got to get rid of that thing. Keep trying to use it. Make an arc. Come up here. Make an arc, and then when I go down to this one, make sure I make the same arc. So there's my intersection. I can draw the angle bisector. Okay, so I just want you to notice something. I'll call this one X. It's a little shorter than Y, isn't it? Okay, well, look down here at side A compared to side B. Is side A a little shorter? Well, it's not just a little shorter. It's actually exactly proportional. So the length of these two sides, so A over B, is going to be the exact same ratio as X over Y. Cool, right? Okay, so that's the angle bisector theorem. What kind of problems might we get with something like this? Angle bisector, this is 7, this is 13, this bit's X, and the whole thing here is 15. Can we find this missing piece right there? Okay, well, it all comes down to, can you name it without using a different variable? You know, if this is A, B, C, D, we don't want to call it AB. We don't want to call it Y. So think about how I'm going to name it without using a different variable other than X. Say it again? Almost. Yes, yes. And a lot of times we do this backwards. We want to say X subtract 15, but the whole thing is 15. This whole thing's 15. Subtract the X bit, and that's the length of AB. So we're naming two different things, but we're using the same variable. So now we can say 15 subtract X over X. What does it equal? Yeah? Okay, so we've talked about 3 different triangle proportionality theorems today. We just talked about the triangle proportionality theorem, we did the 3 parallel lines theorem, and we did the triangle angle bisector theorem. What I'd like you to do is get all 3 of those on a page of notes, and I want to know why they work. There's got to be similar triangles in here. And there's only so many ways that we know we have similar triangles, right? We got angle, angle, we got side, 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 and we got side, angle, side. Side, 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 angle, angle, side, angle, side. All 3 of these proportionality theorems have to work because of one of these three. We've got to have some similar triangles, and we have to know they're similar based off one of these three theorems. I want to know which of those three theorems is for each one. And when we meet together again, I want to look at your notes, see what they look like, and I'm just going to call on random people and see if you know. Don't you hate it when I give you an assignment where you have to think?